So module 6. So module 6 primarily leads with the relationships of stereoisomers. And as we discussed, stereoisomers have same connectivity. Let me draw these two structures right here. The front carbon, the back carbon. The front carbon and the back carbon. Right? Just for my ease, at the back carbon, I'm going to have a staggered conformation. Okay, just at the back carbon. So on the front carbon, I will have a CH3, let's say, a Cl, and a H. Let's say that is what I have here. On my back carbon, I have a H, a Br, and a Cl. Okay. So what is attached to the front carbon? Cl, CH3H. What is attached to the back carbon? Br, H, and a Cl. Now, if I have to figure out relationship between structures, two structures, A and B, let's say on B, at the front carbon, I have groups attached in the same order. Same groups, same order. But in the back, two of the groups have just switched places. Do you think A and B are exactly the same structures? They are not. These are labeled as stereoisomers. So they have same molecular formula. They have same connectivity also. But the groups on any atom are placed. Placement of groups is different three-dimensionally. This is the only difference that we see. So this structure and this structure are stereoisomers. So in this Newman projection, we see that the front carbon with the three groups, which is the fourth bond on this carbon, the bond leading to the back carbon right here. Okay. So having visual aids will definitely help you. Let's look at another example here. Now we know that when we have a cyclohexane, this is my axial location, this is my axial location, this is my equatorial location, this is my equatorial location. If I have a structure like this, and let me say methyl on the axial, and I have a hydrogen here and a methyl on the equatorial, when I will flip it, right? Flip it, what does that mean? I'm making a conformation of my cyclic ring. So this axial will become equatorial and this hydrogen, this equatorial, will become axial. So hydrogen and methyl. Remember, when I flip, the carbon which is pointing up will now be pointing down. So that is why I chose this carbon. On the other hand, this carbon, the equatorial will now become axial and my axial becomes equatorial. Now I want you to understand this. This is conformation. Different energies because of bond rotation. However, did I change the relative position? Both this methyl group and this methyl group are cis to each other. What is the relationship between these two methyls right here? These are still cis. This is going up, this is going up. These are still cis to each other. But if I will have a stereoisomer on the same carbon, I have CH3, I have H, but in here I have H and CH3. Now this H and CH3, I have switched the positions of these relative to each other. I did not switch position of these. So this is exactly the same, but these locations I have kept the same. But now I have made these a different location. So stereoisomers. Now these are stereoisomer. Different energy, definitely. Conformations have different energies. But in this case, it's the same energy. Usually conformations, when you have an eclipse, when you have a staggered, you will see different energy at that point. Not here. But this definitely has, you had to break a bond. You cannot convert into stereoisomers. So you have a cis-trans kind of a orientation. So when we're looking at stereoisomers, remember it is the same carbon with the same groups, but we have arranged them in different manner, three-dimensionally. So in this module, we are going to look at other types of stereoisomers as well with different handedness. One such stereoisomer are known as the chiral molecules. Now, a chiral molecule is not a symmetrical molecule. Okay? There is no internal plane of symmetry. And practically, if we think about it, we only look at the optical activities for chiral molecules. Let me very quickly tell you what is optical activity and why is it necessary for us. Now, when we have regular light, we have to pass it through a filter so it becomes a plane polarized light. This plane polarized light, when subjected to a chiral molecule, so this is my plane polarized light, this is subjected to a chiral molecule, it is a way to determine if something is chiral. If the light stays through the sample, so this is my light, this is my sample. Just like IR, I will prepare a sample. I pass my light and nothing happens. I will say that this is a achiral material. But if the light bends, then I know I have a chiral molecule. So we will see in enantiomeric pairs. So chirality will also have enantiomers. Light can either bend to the left or it can bend to your right. So this is my right and this is my left of the plane. This can only be determined on your machine, on a polarimeter. You cannot do it on a paper. So if your molecule, if your chiral center is going to turn left or is it going to turn right, will be determined only by this. So optical activity helps you figure out or determine if a molecule is chiral or not. For our benefit, we will also look at chiral centers. So when we talk about chirality, you have to know chiral centers. For your course, we will only be focusing on carbon being a chiral atom. So whenever you have a chiral center, we are talking about a carbon atom for our course only. When you go beyond organic chemistry 2, then we'll talk about nitrogens, phosphorus, and other elements also being chiral. So just focus on carbon being the chiral atom. We denote chirality with an asterisk. And there are 3 requirements that a chiral center must have. The first requirement is it has to be a sp3 atom. The second requirement is it must have 4 different groups on it. And the last requirement, and it has to fulfill all of these requirements, there should not be any symmetry. It should be non-symmetric. Point or plane. So it has to fulfill all of these. So if you think about a carbon, a tetrahedral carbon, all tetrahedral carbons with 4 bonds. So what is sp3? It just denotes you have 4 electron domains or densities around. And that's why you have to figure out or must have 4 different groups around it. Let's focus on this carbon. This carbon has a hydrogen. This carbon has a OH and a Cl and a CH3. So when you start to look at a carbon, look at the atom which is directly attached to your carbon of interest. And looking at all of these, we see all of these are different groups. This carbon is sp3. It has 4 different groups. There is no point of symmetry. This carbon is chiral. What about this? 1, 2, 3, 4 carbons, right? All of these carbons have all of their 4 bonds. I'm not showing the hydrogens, but that does not mean that there are no hydrogens on it. And so on this carbon, what do I have? I have 3 hydrogens. All of them are same. So this is not a chiral atom. Not a chiral atom, not a chiral atom. Why? Even though it has a methyl and an ethyl on one and other side, it still has 2 same groups on it, 2 same hydrogens on it. Not a chiral atom. What about this? Yes, there is a methyl group and ethyl group. 1 chlorine. What is the 4th bond? The hydrogen, the hidden hydrogen. Where is that hydrogen? Because my chlorine is coming out of the plane, my hydrogen will be going behind the plane. So this is a chiral atom. What about this? Not chiral, not chiral, not chiral, not chiral. What about this? Is this chiral?
No.
No, it is not. Very good. Why?
There is 2 methyl same.
Same groups, exactly. So even though I have hydrogen and hydroxy to be equivalent, different groups, my ethyl is exactly same. So this is not a chiral site. Okay, very good. Let's look at this structure. Now this is a ring. In a ring also, I can have chiral sites. So for example, definitely not chiral. Why? Because it has 2 hydrogens, same groups, same groups, same groups. But what about these 3 other carbons? Remember the first requirement, all of the atoms which you are planning to be chiral have to be a sp3 atom. sp2, sp2. So these are definitely not chiral. But what about this bromine containing carbon? I have a cyclic ring here, and I have this bromine here. I have this hydrogen here. Remember the hidden hydrogen. If it is not, if my group is coming out, my hydrogen will be going at the back. So is this carbon chiral or not? And so let us look around the ring. We know this is different, this is different. Let's look around the ring. There is this carbon atom A, and then there is this carbon atom A. Remember, I told you to look at the first atom which is directly attached to your carbon of interest. So looking at the carbon of this interest, we see I can label all the atoms which are directly attached to my carbon of interest. Remember, this is not proven to be chiral yet. So my carbon of interest has these atoms directly attached to it. These two groups are exactly the same. So they are not helping me figure out any distinguishing or any differences. Let me look at the next atom. So from here, this is my second atom. From here, this is my second atom as well. Any questions? How did I label them as next atoms? So from here, when I'm walking from here, I am seeing, this is not electron density. This is just movement of my carbon for seeing only. Any questions? How did I label them CA and CB? Okay, good. So now I see that this carbon has sp2 hybridization while this has sp3 hybridization. So definitely this side is a little different than this particular side. And so all the four groups on this carbon are different. I can label this as my chiral center. Okay, so you have to scan the whole molecule from one end to the other. If you look at stereo isomer, different projections, a chair conformation, I can see chiral centers here and here also. Why? On this carbon, I have carbon A, carbon B. On this carbon, I have carbon A, carbon B. This carbon B has what? It has two hydrogens and a carbon. What does this carbon B has? This carbon B has an oxygen, a hydrogen, and a carbon next to it. And so this carbon is chiral. Similarly, I will do for this particular carbon. Now, because I'm looking at a different carbon, my carbon atoms A and B will change. Because I'm focusing on this, this will now become my A, this carbon will become my B. Walking from here, this carbon will become my A, this carbon will become my B. And the B carbon, what do I have? I have a hydrogen, a oxygen, and a carbon. So you have to walk away from your carbon of interest. Now you don't have to, but no, it's in your drill section, I think. In your drill section, I have sequence sheets. You can use those if you are comfortable using them. So I have listed out these rules there. So how do we recognize an optically active carbon or a chiral carbon or a stereochemical carbon or a stereocenter or a stereogenic carbon? This is how. So you look at the carbon of interest, then you keep walking away from each side. You walk away, walk away, walk away, walk away, till you see the first difference in that structure. So the directly attached atoms, you can label them as anything. I label them as A. The second next things, you can label them as B. When you're comparing one set, compare exactly same sets. Don't compare A's and B's. Only compare A with another A. Compare C with another C. You cannot compare A and C. So that is why we label our structures. Okay. Now with each chiral center, there are possible stereo Isomers. How many stereoisomers are possible for a chiral molecule? If I have a molecule like this, how many chiral centers do I see? I see only one chiral center. And so number of chiral centers is n. 2 raised to power 1 equals 2. In this particular structure, how many stereoisomers will be possible for this particular structure?
4.
How many chiral atoms do I have? 2. And so, yes, 2 raised to power 2 will be 4. So for this structure, I can have 4 possible stereoisomers. Any questions so far? So if we look at our slide right here, we see how stereoisomers can be drawn. This is done by interchanging any two groups of the chiral center or the chiral carbon. Now, let me show you an example of how this will be done. And we'll come back to this slide. Okay. So when you will interchange any two groups, you are going to change the three-dimensional look. So I have a carbon. Let's say this group is going back. This is my first V. Both of these two groups are in my planar bonds. These are my planar bonds, dash and the wedge. So this is CH3. Let's say this is H, this is Br, and this is O. When I will redraw it, make sure that you redraw the orientation exactly the same. What do I mean by that? Can I draw it like this? No. Can I draw it like this? No. You have to keep the center as it is and then see relative locations of these bonds, how it has been drawn on your original structure. So when we look at a molecule or an atom three-dimensionally, keeping the same orientation, let me change any two groups. What does that mean? I'm going to keep these two groups as they are. Hydrogen stays on this planar bond, methyl stays on this planar bond. But I'm going to switch the location of these two groups. So OH and Br. Now this is helpful if we will have our models. Okay. So I'm just going to keep one group exactly the same. So this is my group with blue atom coming out, green and red in the planar bonds, and my white at the back. So what did I do here? I just made one change. If I look at these two structures, their connectivity is exactly the same. Their spatial arrangement around the three-dimensional arrangement, that is also exactly the same. So what did I do? I just kept everything exactly the same. I will switch these two groups. I kept the location of all the others exactly same. So green is where it was, red is where it was, but I switched these two. This is how I create a stereoisomer. So three-dimensionally, the arrangement of the groups around the central carbon will be different. Okay. So with one carbon atoms, how many chiral atoms do I see? N equals 1. We just did this. we will see two stereoisomers. So one stereoisomer is here, the other is right here. What would happen if I have two? At that point, all of you are able to see this? Oh. And I'm just drawing my sideway dash and wedge kind of a projection. In the planar, let me keep X. In the wedge, let me keep Y. In the dash, let me keep Z. So X, Y, and Z, right? And just for the purpose of our ease, I'm going to write them as X prime, Y prime, Z prime for the atom of C prime. It's exactly the same. I just want to see us the difference. So how many chiral atoms do I have here? All of these four groups are different on this carbon. So this is a chiral atom. And on this carbon, all of the four groups are different. So this is a chiral atom, right? How many stereoisomers should be possible now? 4. Let's draw them. I'll draw them for you. I'm going to keep this part exactly the same. So C, Y, Z, X. The C prime stays the same. The orientations stay the same. Did I change the orientation? The planar bond, dash, and the wedge. Planar bond, dash, and the wedge. I'm going to keep my Z where it was. And I will switch X and Y prime. This is my stereoisomer respective to this. What else can I do? Keeping them exactly the same, I can switch these two. So now, keeping them exactly the same, keeping the orientations exactly the same, C prime, X prime, Y prime, keeping the orientation here also exactly the same. I'm keeping X where it was, but now I'm switching these two. So earlier I switched these two. Now I'm switching these two. So Z goes to the place of Y. Y goes to the place of Z. See how I switched it. This is my third stereoisomer. Another stereoisomer. Remember, I have to make up to 4 possible stereoisomers. Don't worry, I will not ask you to draw all the isomers, but you should be able to recognize them. They are not exactly same structures. That is what you need to understand. So now I'm going to keep the carbon exactly the same. First I had switched from this. Now I will switch from this. So C prime, X prime, Y prime, Z prime. Orientation exactly the same. Keeping my X where it was. I'm going to switch these two guys. Y and Z. And you can switch any. You can switch any, and we will see that it comes to all of these structures. And I'll tell you how these A, B, C, D are related to one another. But remember, only one switch per carbon. Here we did only one switch. What will happen if you do a second switch? When you will do a second switch, let's look at this molecule. This molecule, my original molecule, and I had switched these two only, the location of these two only. So the arrangement, if I look across this, I have a mirror image kind of a thing, right? So this is my original molecule. This is my one switch molecule. What if I switch this one more time? Any two groups. Salome, are you here?
Yes, ma'am.
Which two groups would you like me to switch on this structure? On the stereoisomer of my original one, which two groups? I'm giving a big responsibility here, Salome. Go ahead and tell me any two groups, whichever you like.
I guess the red
Mm-hmm.
and the green.
Okay. And this is randomly, right? Randomly, Salome has decided that let me switch one more groups. So we made our first switch and now we are making our second switch. When we make our second switch, we will generate our original molecule. So did I make 3 stereoisomers or still I have 2 stereoisomers possible? I still have 2 stereoisomers possible. I had the stereoisomer and now I have my original molecule. Okay. So remember, when you have to make a stereoisomer, only make one switch. When you have to generate your exactly same molecule, that is the time that you make your 2 switches. So 2 switches will give you your original molecule back. Now, before we jump into the types of stereo center, let's look at some R and S configurations. And this is very important for us when we are looking at our relationships. Now, if you remember a few minutes ago, we had looked at the right rotation and the left rotation. And I told you these rotations, so plus or dextro-laboratory and minus or levo-rotatory to the left, these directions can only be figured out experimentally. You cannot do them on paper. But R and S configurations are something that we can do on paper. One more thing that you have to remember, R and S have no correlation with plus and minus. There is no correlation. If in one enantiomer R is negative, in the other enantiomer, the R may be positive. Okay, so there is no correlation between these two numbers. All right, so to look at this, I'm going to go back to our sequence sheet. Okay. So on our sequence sheet, we will see the sequence of how to figure out R and S. The first thing that you must do whenever you're looking in a molecule about awarding it a R or a S enantiomer is that your carbon must be chiral. Whichever carbon is chiral can be assigned a R or S on it. So make sure that you understand that part first. So how will we do that? Make sure all these requirements are fulfilled. The next thing is that you prioritize your 4 different groups, and this will be based on the atomic number of what? Of the atom which is directly attached to your carbon, which is chiral. Okay, remember, priority has nothing to do with the bulk, only the atomic number. Okay, the next thing that we have to do is compare similar atoms. Don't compare different atoms, as I was mentioning to you. And in all your groups, you have to give numbers. So priority numbers from 1 to 4. Highest priority to 1, lowest priority to number 4. So looking at our lecture slides back, let's see how priorities are figured out. So remember, we have to look at the atomic number. If you have a carbon, let's say that we have a carbon in this particular example, which is the atom directly attached to our chiral carbon. I'm going to label them as atom A. When I look at atom A's and I look in my periodic table, I see that out of all of these atoms, bromine has the highest atomic number, followed by oxygen, followed by carbon, followed by hydrogen. So highest atomic number is bromine. I'm going to label this group as number 1. This is my second priority. This is my third priority. This is my fourth priority. Okay, so this is what I need to do. So your job is, first of all, to identify high priority groups. If you look at these groups, which I am going to draw, which of these will have more priority? What is pH? pH is a phenyl ring. Now remember, there's a difference between a benzyl, which has a CH2, and a phenyl. A phenyl just has a benzene ring on it. So this is a benzyl. pH indicates a phenyl. So if OH is attached to a carbon or a benzyl is attached to a carbon, out of these two, who will have more priority? And then if you have a OH or a OCH3, so I'm just replacing a hydrogen with another carbon, who will have more priority? If I have a bromine or a, let's say, molecule like this. What is this? I'm just writing it in a condensed manner. You know what? Go ahead and write these structures on your page also. So this will look like CH2, CH with 2 CH3s, right? So remember, when I make a bond like this, I am trying to say on a carbon, if this is attached, and on the same carbon, if this is attached, who will have more priority? And let's say if you have an NH2, or if you have a hydrogen with a oxygen, who will have more priority? So this is, remember, on the same carbons, same carbons. Did everybody write this out? Okay, so how about we do a poll quickly, and let me see how many of you are able to figure out who has a higher atomic number. Remember, you don't have to look at the atomic bulk. You have to look at the atomic number of the atom which is directly attached to it. If you're not able to figure out from the same atom, you jump to where? To the next atom, to atom B. So which of the following relationships? And I'm going to launch a poll which will read the question as, which of the following relationships of group on the same carbon? Remember, these on the same carbon, this on the same carbon, this on the same carbon. I'm writing a wrong structure, a wrong answer here. Let's see how many of you can do that. So which of the following relationships of groups on the same carbon is wrong considering priority of the group? All of you have copied this? Anyone who still needs to copy it? Okay, so your poll is active, and read carefully. I'm going to give you at least 2 minutes. Same groups that we have discussed right now. That's the one that we are doing. Okay. Mm-hmm. Think about it. We are looking at this carbon and this carbon. So only one of these options is wrong, and you have to choose the wrong option here. Not all of the options, or not just any option. I have asked you to choose the wrong option. So you have to be able to identify which is the more priority group. Okay. So the 2 minutes will be over in 7 seconds, and then I'll give you 10 extra seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And that's the end of it. And most of you have chosen that OH being more prior to OCH3 is wrong. And that is the correct answer. When you compare H and C, this is going to be a more priority group. But the another answer that you could have chosen, and which is very close, is the one where you have NH2 and N double bonded O. If you look at this nitrogen, double bonding just means that your nitrogen is attached to the same atom twice. And so if you compare from hydrogens, oxygens definitely have a higher atomic mass. And so this group will have more priority over NH2. In this part, definitely oxygen and carbon. So oxygen will have more priority. Between bromine and CH, definitely bromine will have more priority. Okay, so I'm glad that nobody chose the other answers, which were not the answers at all. So once you figure out your priorities, then, and you are able to number them, then you have to follow the instructions where we have to look at, or where we have to assign number 4 at the back. So make sure that your number 4 priority group has to be at the back. Okay, so if you look at this particular structure, among all of these groups, chlorine, hydrogen, carbon, and this carbon, chlorine will have the highest priority, hydrogen will have the least of the priority. So this is your atom A, and this is your atom A. Your atom A has 3 hydrogens, while this atom A has 2 hydrogens and 1 carbon. So this is attached to this carbon. Who will have more priority? Definitely ethyl will have more priority over methyl. Who does not understand this part? Okay. So once we have our priorities assigned, you can do 2 things. The first is use your model. Let's say that this is the model that we are using. where white is our hydrogen. Okay? And you can assign that, okay, one of them is our CH3, one of them is our ethyl, and one of them is our OH. So I'm holding on to my number 4 at the back, and I'm only looking at these guys. So OH, ethyl, and methyl. So 1, 2, and 3. And so reminding my kindergarten skills, I will go from 1 to 2 to 3. And so what is this rotation that is happening? This is a clockwise rotation. And so according to my annotations right here with 1, 2, 3, this should be considered as the R configuration because it is moving in the clockwise motion. I'm not sure if some of you might be seeing it in the mirror form and I might be rotating in the other way, but I was rotating it clockwise. So if I rotate it clockwise, it has to be R. Okay, let's do it with the molecule here right away. So my H is hydrogen, which is the white bulb. My blue will be my methyl. My red will be my ethyl. And instead of hydroxy, I have a chlorine as my green molecule. And so 1 goes to 2, goes to 3. So now I'm rotating it anti-clockwise. Holding my number 4 at the back, I'm rotating it anti-clockwise, which is a S according to this particular structure. Could you all see my window, the small window? Could you all see my atom moving here? All right. So not just with these, you should be able to give your configurations to bigger structures as well. Okay. Let's do it for an example here. Let's say that I have a structure like this. Okay. How am I going to draw its stereoisomer? First of all, I will just know that I have these hydrogen and chlorine. I'm going to just switch their location. Oh, actually, yeah, H and chlorine. So my chlorine earlier was going back. Now my chlorine is coming out. So I have made a stereoisomer. I just switched their location. One switch creates the isomer. Let's look at the configuration here. At this carbon, I definitely have a chiral center. Ethyl group, methyl group, chlorine, and a hydrogen, right? So my chlorine will get number 1 priority. Hydrogen will get my number 4 priority. Ethyl will get number 2 priority. Methyl will get number 1. And I can redraw this structure. From this carbon, I will keep my orientation intact. And I just write the numbers. 4, the chlorine was at 1. So I'm keeping my orientation intact to figure out my RNFs. Once I have given my priorities, I have to make sure my number 4 is at the back. Is my number 4 at the back? It is not. So we already looked at how to use a model to move this at the back and rotate it the way we want it. But what if you're not able to see it with models? And that's completely fine. Then you make 2 switches. And I'm going to take baby steps for now. I'm going to draw 2 more of these, and I'll tell you why. Same orientation, okay? First switch. My first switch will create the stereoisomer. And I will tell you why I wrote enantiomer in a few minutes. Let's keep 1 and 2 where they are. And let's switch 4 and 1. Why are we doing that? so that we can take our number 4 at the back. Now my number 4 is at the back. Is this molecule my original molecule? It is not. So I will do my second switch. Remember when I showed you with these two, I had shown you that you need to do 2 switches to get your original molecule. So I have brought my number 1 and 4 at the back, and I definitely want to keep my number 4 at the back. All right, let's see. Hannah, are you here?
Yes, ma'am.
Hannah, I need your help. Are you following what we are doing right now? We are making switches. I just switched these two guys, leaving the other two right here. Now I want to make a second switch. From this structure, I want to make a new structure where my number 4 is still at the back, but I need to make one more switch between two groups. Please suggest which two groups we should switch. And you can switch any two groups. Remember, we need to keep 4 at the back. Do you want to switch 1 and 2? Do you want to switch 1 and... I'm sorry, I think I did a bow here. This is 3. So should we switch 1 and 2? Or should we switch 1 and 3? Or should we switch 2 and 3?
2 and 1.
Okay. Thank you very much. So I'm going to switch 2 and 1. And you can switch any group as I was telling you. And so keeping my number 4 at the back, I can completely ignore it. 1 goes to 2, 2 goes to 3. And what kind of a motion do I see here? I see a anti-clockwise motion, and hence this is going to be my S enantiomer. On the other hand, let me look at this one. Remember, I made one switch. What will be the enantiomer right here? So these two are exactly same things. You know why? Because I made one switch here and I made one switch here. So these two are exactly the same compounds. These two are exactly the same. These two are exactly the same. These two are exactly the same. We're just looking at them differently. So if you look at this, my number 4 is at the back. I can completely ignore it. 1 goes to 2, 2 goes to 3, 3 goes to 1. What kind of a rotation am I getting here? A clockwise motion. And this is what my R is. Do y'all understand how did I awarded it an R or S configuration? And we'll do
Yes,
more
ma'am.
examples. We'll do more examples. Thank you, Hannah, for your help also. So the first kind of stereoisomers, after we are done and know how to do the R and S configuration, are enantiomers. Enantiomers always exist in pairs. To one, there is the other. To a S, there will always be a R. To a RS, there will be a SR. Okay, they always exist in pairs. They are non-superimposable. What does that mean? Now, best example of enantiomers are our hands. You know, they are mirror images of each other, but non-superimposable. You know, my thumbs stick out whenever I try to superimpose them. But if I try to superimpose them like this is not superimposing. This is known as superimposing. This is just mirror imaging. So they are mirror images, but non-superimposable. Okay. let's look at a very complicated structure, or at least in the beginning, it might look like a complicated structure. Let's say I have a molecule like this, and I have a group here. So I have this structure, and I need to draw its enantiomer. What is the enantiomer? A mirror image. A mirror image which is non-superimposable. So I can draw my enantiomer like this. At each carbon, I have to make sure I draw a opposite orientation. So this and this, I can easily identify them to be my enantiomers. But what if I had to draw a same compound but flipped? I can draw the same compound flipped. In this orientation, my OH was going at the back. In this orientation, my OH is coming in the front. In this orientation, my molecule methyl is going at the back, coming front. And in this, it is coming right here. This is my same structure. This is my enantiomer. Now, this is one of the ways by which we look at structures, and you can have different versions for complicated looking structures. So how would you always be sure that you're writing the or drawing the same thing? So very quickly, let's do a R and S right here. So go ahead and draw this out with me. I'm drawing the planar structure. So I drew up a line between two carbons. Then I drew a planar bond here, and I want to draw a planar bond anti to this. I'm drawing out my wedge here, so I have to draw out my wedge here, and I'm drawing it like a tetrahedral kind of a shape. Not exactly there, but somewhat. Okay, so please make sure that you all are drawing with me. This is CH3. This is NH2. This is C2H5. This is Br. And let's make this a OH. And this is a CH3. Okay, please make sure that you draw the correct orientations. Okay. So what if I'm giving complicated structures like this? Don't be scared, first of all. We will be following another sequence. And that is also in your sequence sheet if you are not able to copy it because of space constraints, but make sure you draw these structures out. The first thing that you must do whenever you're asked to figure out relationships is to know the molecular formula and HDI of both the molecules. What is the molecular formula for this? What is the HDI for this? What is the molecular formula for this? What is the HDI for this? If both of those things are exactly the same, you know you have a stereoisomer. Then, what is the next step that we will do? We will have to make sure that the connectivity is same or different. And so if the connectivity is exactly the same, and let's see how is this the same. Will I be counting my number 1 from this chain, or will I be counting my number 1 from this end? So remember, this is where your module 4 is going to help you. You should be following the path. First, find the longest chain. This is no doubt your longest chain. Where are you going to start your numbering from? Closest, so that you have the lowest locant number. So I have 1, carbon 2, carbon 3, carbon 4 and 5 on this ethyl. On this structure, where is the connectivity? Where am I going to start my numbering from? First, I identify this to be my longest chain. And then I see that this is carbon 1, carbon 2, carbon 3, carbon 4 and 5. So on carbon 2, I have a Br and I have a OH. On carbon 2, I have a Br and I have a OH. On carbon 3, I have a methyl and a NH2. On this carbon 3, I have a NH2. And what is this here? This is the CH3 or the methyl group. Any questions? So the connectivity is also exactly the same. So I know that I have stereoisomers now. The next thing that you must do is assign R and S if chiral centers are there. Okay, if the connectivity is the same and you have chiral centers, then you assign R and S. If you have double bonds and or rings, then you look out for geometrical isomers or cis-trans isomers. So in here, we don't have any double bonds or triple bonds. Double bonds or rings. We just have sp3 carbons. Chiral here, chiral here, chiral here, chiral here. So I'm going to give you all of you a few minutes to figure out what is the configuration of these carbon sites. And I just want to redraw it here so I can see better myself. Your OH, CH3. So let's take it one at a time. On my first structure, I have these 2 carbon centers, but I will focus on this carbon first. Which atoms are directly attached to this carbon? This atom, this atom, this atom, and this atom. And so among the bromine, oxygen, and the carbons, I know bromine is definitely going to be my number 1. Among the carbons and the oxygen, I know my oxygen is going to be my number 2. But among these 2, who's going to be my 3 and who is going to be my 4? So I see that on this carbon, I have 3 hydrogens, while on this carbon, I have a carbon. So this carbon A has 1 carbon, 1 nitrogen, and another carbon right here. Any questions? So I'm only focusing on this carbon right now. So among these 2 groups, which group will be more priority? This group right here will have more priority over that group. So I'm going to redraw the orientations. Oh, I don't have to write the orientation. I just write the number associated with that bond. And please see I did not change the orientation. If the two planar bonds were drawn like this, I drew them like this. The wedge is coming here, the dashes are going in the back. The wedge is coming here, the dash is going at the back. I did not change the orientation at this carbon. And I'm going to do two more structures. And remember, this is just at the beginning. So my first switch. Do I need a switch, first of all? My number 4 is not at the back, but it is at a planar bond. Do you think I should still move it? Absolutely. Because you're just starting out with stereochemistry, if you're not able to locate in the models, I would strongly encourage you to bring your number 4 at the back. So I'm going to make these switches. Number 4 goes here, number 2 goes here. 3 and 1 stay where they are. Now this making first switch gives me the enantiomer. I need my original molecule. And so I'm going to keep my number 4 at the back and I will switch any other two groups. So usually what I do is, if I have moved 2 and 4, I will then move 1 and 3. So right now I'm keeping 2 and 4 where they are and switching 1 with 3. Any questions on what is being done here? I'm going to cross it out. 1 goes to 2, 2 goes to 3, 3 goes to 1. This is an anti-clockwise motion, and this carbon is a S. Everybody good? Now I'm going to focus on this carbon. And if I want, I can redraw it to see it better. So what I did here was, instead of writing C2H5, I wrote out the CH2, CH3. Okay. So this is the carbon now, which I am interested in. This carbon right here. This carbon right here. So there is this carbon, and I don't have to care for this carbon. Because I'm focusing on this carbon, I don't have to look at the geometry of any others. There's a bromine here, there's an oxygen here, there's a carbon here. That is the only thing that I'm interested in this carbon for now. Because this is my, relative to this is my atom A, this is my atom A, this is my atom A, and this is my atom A. So notice when I was looking at this carbon, my atom A's were different. And now that I'm focusing on this carbon, now my atom A's are completely different. So that is a possibility, and that is what you must do as well. So looking at all of these 3 carbons and a nitrogen, who will have more priority? The nitrogen, who has a little higher atomic number, will be my group 1. Among these 3, we see that this carbon A has 2 hydrogens and 1 carbon. This carbon A has 3 hydrogens, whereas this carbon A has a carbon, an oxygen, and a bromine. So among all of these 3 groups, this carbon group will be highest priority. So we have listed 1, this will be our 2. Among these 2, this will be our more priority, and this will be the last of the priority. 2 separate carbons, 2 separate orientations. I'm going to draw my orientation from here. NH2, I don't have to write my NH2. I just write my numbers 1. And then on this wedge, I have number 4. On this planar bond, I have 3. On this planar bond, I have 2. So what is the next thing after I have assigned priorities? I have to make sure my number 4 is at the back. Is my number 4 at the back? It is not. And I'm going to draw these again. Now pay attention, I'm going to do a different thing that you have not seen it yet. On 1 and 3, I'm going to switch between 4 and 1. Why? Because I need my number 4 at the back. So I'm going to keep my number 2 and 3 on the same location. But I'm going to change 1 and 4. Now instead of drawing my third structure, I just go first switch. And then right now I'm using a different colored pen so you can see what I'm going to do. I can switch any other group. I have already switched 1 and 4. I'm now going to switch my number 3 with number 2. So on the same structure, I'm doing this. Okay, I was taking baby steps here just to show you how I would do it. But I'm here drawing out our on the same structure. Okay, don't be scared. Number 4 at the back, completely ignore it. So when did I do my second switch? This is my second switch with my red pen. 1 goes to 2. Remember, this is my new 2. Goes to 3, goes to 1. What is the kind of rotation that I'm seeing here? I'm seeing a clockwise motion. So this carbon is a R. Very good. Now with this information, that how I'm going to divide one carbon and the 2, let me draw the other molecule also. And though it looks like a different shape, you don't have to be scared. I'm going to copy it. Here, OH, NH2. Okay, it's exactly the same that I have here. Now I will tackle this one at a time. There are 2 carbons. I can start from either of them. Let me start from the carbon 2 because I started here also at carbon 2. So remember, we are doing RN assignment only after we have confirmed same connectivity. If they are different connectivity but same molecular formula, we know they are constitutional isomers. So looking at this, where is my orientation? I'm going to do my orientation. Remember, this is my dash wedge bond. Keeping my orientation intact. Okay, I'm focusing on this right now. Br will be my number 1. O is my number 2. Methyl will be my number 4. And this bulky group is my number 3. Now look, instead of drawing these 3 structures or 2 structures, I'm going to do it on the same carbon. Don't be scared. Just keep attention on my pen. What is the first thing that I need to do? I need to move my number 4 at the back. So 4 comes here and 2 comes here. And then I can switch any of these 2 groups. Let me switch 2 and 1 or 1 and 3. So I'm going to make this as 3, this as 1. Now, ignoring my 4, 1 goes to 2, 2 goes to 3. And what is this conformation going on? This is a anti-clockwise, very good. And so this carbon has to be assigned a S. What about this carbon? I will follow exactly same route. Keep my planar bonds where they are, dashed and wedges where they are. Because I have already done the priorities here, I can use that here also. NH2 will be my number 1 group. So NH2 will be my number 1 group. The methyl will be my number 4 group. This bulky thing will be my 2nd priority group, and the BR, I'm sorry, not the BR, this part, the ethyl group, will be my priority 3 group. Who does not understand what I did? I just used this carbon and this carbon because the priorities are same. I just used that. I don't have to redo that. Okay, on this carbon has priority, ethyl has a priority of 3. That's why I gave ethyl, this planar group, a priority of 3. And so my number 4 needs to be at the back. Number 4, number 1, number 2, number 3. So I switch these two first, then I switch these two. So ignoring number 4, 1 goes to 2, 2 goes to 3, 3 goes to 1. What is this motion? A clockwise motion, and I have a R. So looking at our structures, don't be scared with what look they have on them. Okay, you don't have to be scared because of that. But this R and S assignment on these structures, A and B, will help us. And from this page, I'm just going to copy out. This is my S. This is my R. This is R. This is S. So we usually assign these configurations next to the carbon, the chiral atom we are looking at. So what is the relationship between these two? Remember, enantiomers always exist in pairs. So what you have to do is, you have to compare at C2 and C3 in A, what is the configuration? At C2 in A is S, a C3 in A is a R. In structure B, at C2, what is your configuration?
S.
S. What is the configuration at C3?
R.
R. What do we see? Exactly same configurations. And so even though these two structures are drawn differently, what is the relationship between A and B here? It is same. So do you see how R and S are going to help us? What if instead of this structure, and I'm going to copy it up. So what has happened between these two structures? Between these two structures, I have flipped the structure horizontally. Whereas my bromine was starting from here. If I start from here, number 1, 2, 3. Now I will be starting my counting from 1, 2, 3, 4, 5. My bromine was at the wedge. Now my bromine is in the dash. My NH2 is in the dash here, but it is now in the wedge. And so is my methyl. Now, if you can recognize on paper that this is a flipped structure, you will know that these two are exactly same as well. But if you're not sure, this is where you will assign R and S to your chiral sites, and you will know whether you have same structures or if you have a enantiomer. Let me draw the enantiomer. The enantiomer would look something like this. And instead of having a R, let's quickly do this. What would be the orientations here? Where's my paper? And so the priorities will be similar. Just copying it. So I was just copying this here. At this carbon, this group is going to be my number 4. This group NH2 is going to be my number 1. This ethyl group is going to be my number 3. And this big bulky group is going to be my number 2. And so there is another way. If you have number 4 coming out, whatever direction you go to, you can just look at the opposite direction. So right here, I have 4, 1, 2, and 3. So this means I'm getting a S, but you have to look to flip the 4 number and the 4th number. But some of the students do get confused in it. So I would still suggest to keep or switching your bonds. So this will be 3 and this will be 2. Ignoring number 4, 1 goes to 2, 2 goes to 3. So this carbon right here will become a S. And this carbon, oxygen bromine. Bromine is going to be our number 1. OH is going to be number 2. Methyl is number 4. This planar bond is going to be number 3 for this carbon. Number 4 is not at the back. 4, 2, 1, 3. And so ignoring my number 4, 1 goes to 2, 2 goes to 3. I have a clockwise motion, so this will be a R. This is an R. So looking at our original molecule, remember this is a S and this is an R. What is the relationship between my C and D? Remember, A, B, and C. They are just different ways of looking at the same molecule. And now D, how do I compare these with this D? So in C1 and C2, I have to look. In A, what do I have? I have a S, I'm sorry, C2 and C3. I have a S here and I have a R here. And what about in D? What do I have in C2? I have exactly opposite R, and in C3, I have exactly opposite S. So what is the combination that I see here? I see a SR here, and I see a RS here. C2 is R, C3 is S. C2 is S, C3 is a R. Because I have exactly opposite locations here, I will say that C and D are enantiomers. if C will rotate the light to the left, D will rotate the light exactly to the same extent, but in a opposite direction. And so the relationship between enantiomers will always be in an opposite configuration. If you will have just one chiral center, you can make one enantiomer. If one is R, the other will be S. Opposite. If one is SR, the other enantiomer will be RS. If one is RR, the other enantiomer will be SS, and so on and so forth. But at each similar carbon site, so we compared C2 with C2, not C2 with C3. So at the same carbon sites, you have to compare that what is the configuration, and if it is exactly the opposite for each of the locations, then we say we have an enantiomer. Okay, so let's stop our class today here.